Every single day, more than 100 new software vulnerabilities are published to the world. Last year, over 40,000 of them. They land on your code, your dependencies, your containers, your cloud, whether you're watching or not. And somewhere in that flood is the one that ends up in a breach report with your company's name on it. Most teams respond by patching whatever has the scariest score that week. It feels like progress. It isn't. You burn out your engineers, you chase vulnerabilities nobody will ever exploit, and you still miss the one that mattered. The problem was never a lack of effort. It's the lack of a system. This is a complete, practical guide to vulnerability management for a modern cloud-native company. Not a tool tour, a methodology. How to find what's wrong, decide what actually matters, fix it on a deadline that fits the risk, and prove it's working. And at the center, we'll go deep on how to run a rigorous vulnerability assessment. Let's build the program. Here's the map for the next 40-odd minutes. We'll define the discipline, then build it in order. The lifecycle, our example product and where its weaknesses hide, how to plan the program, how to inventory what you're protecting, the assessment methodology in depth, how to prioritize, how to remediate, how to verify, and how to measure and govern the whole thing. Stick around for the end. There's a checklist you can take straight back to your team. First, let's clear up 3 terms people mix up constantly. A vulnerability assessment is the act of systematically finding and rating weaknesses across a defined scope at a point in time. Vulnerability management is the continuous program that wraps around it. Assessment plus prioritization, remediation, verification, and metrics running forever. And a penetration test is a goal-driven simulated attack that proves whether specific weaknesses are actually exploitable. Assessment finds the doors. Management makes sure they get closed and stay closed. The pen test kicks a few to see which one's open. Why does the distinction matter? Because a scan is not a program. Plenty of companies buy a scanner, generate a 10,000-line report, and call it vulnerability management. 6 months later, nothing's fixed, and the report is bigger. We're building the program. The assessment is one chapter inside it, but the program is what actually reduces risk. Vulnerability management is a loop, not a project. 6 stages. First, asterisk inventory. Know what you have. Second, discover and assess. Find the weaknesses across all of it. Third, prioritize. Rank them by real risk, not raw score. Fourth, remediate. Fix, mitigate, or formally accept. Fifth, verify. Prove the fix actually closed it. Sixth, report asterisk. Measure, learn, and feed it back. Then the loop turns again. Forever. The word that makes this work is continuous. A vulnerability assessment is a photograph. Vulnerability management is the film. Your code ships daily. Your dependencies change weekly. The threat landscape shifts hourly. A point-in-time audit once a year tells you almost nothing about your risk today. The loop has to run at the speed of your software. And for a cloud-native shop shipping many times a day, that means automation is not optional. But continuous doesn't mean everything, constantly, at maximum cost. Tune the cadence to the risk. Your internet-facing, Tier 1 services get assessed on every commit and continuously in production. A low-traffic internal tool can be weekly. New CVE feeds, though, are matched against your existing inventory the moment they're published, because a component that was clean yesterday becomes vulnerable the instant a new CVE drops against it, with no change on your side at all. Risk-based cadence is how you stay continuous without burning infinite compute and attention. And every stage needs an owner. A vulnerability with no name attached to it is a vulnerability that will still be open next quarter. We'll come back to ownership when we plan the program, but plant the flag now. Tooling finds problems, people and process close them. Let's make this concrete with a realistic product. Meet Nimbus, a business SaaS. It's not one app, it's a dozen microservices. A Spring Boot service in Java, a couple of Go services for the high-throughput paths, a Python fast API service for data processing, a Node.js front-end API, and a Kotlin service the mobile team owns. Each one is built into a container image. They all run on Kubernetes. And to serve customers in different regions and meet their procurement demands, the same platform is deployed on Azure's managed Kubernetes, AKS, and Amazon's, EKS. Now here's the key mental model for the whole video. That one little service is not one thing to secure. It's 7 layers, and a vulnerability can live in any of them. There's the code your engineers wrote, the open-source dependencies they pulled in, the base image the container is built on, the infrastructure as code that provisions it, the Kubernetes configuration that runs it, the cloud account it all sits in, and the running workload itself, live in production. 7 layers. Multiply by a dozen services times 2 clouds. That's your attack surface. Let's make each layer real. In asterisk your code, a SQL injection in the Java service, an SSRF in the Python one. In dependencies, a critical CVE in a logging library you've never heard of, pulled in 3 levels deep. In the base image, a years-old vulnerable system package nobody updated. In infrastructure as code, a storage bucket set to public in a Terraform file. In Kubernetes, a pod running as root with no network policy. In the cloud, an overpermissive IAM role that can read every secret. And at runtime asterisk, a container quietly making outbound connections it never should. One product, 7 very different kinds of weakness, each needing a different tool to find it. And there's a multiplier we can't ignore. Nimbus runs on 2 clouds. That's not just twice the servers. It's 2 completely separate identity systems, 2 networking models, 2 sets of managed Kubernetes defaults, 2 registries, 2 audit logs. Every misconfiguration you can make once, you can now make twice, differently. Teams running multi-cloud almost always have one cloud that's well-tended and one that's quietly drifting. A rigorous program treats them as one scope with 2 implementations. Never the cloud the security team happens to know best. This is why we run a scanner is never enough. No single tool sees all 7 layers. A rigorous program needs the right lens on each layer and a way to bring all the findings into one place, which is exactly what we're going to build. But before any tooling, you have to decide how the program runs. That's planning. Tools are the easy part. The programs that actually work start with decisions written down, a policy, not a 50-page binder nobody reads, a 1-pager that answers 5 questions. What's in scope? Who owns what? How fast we fix things, by severity. When we're allowed to not fix something. And how we measure success. Get those 5 answers agreed and signed by someone with authority, and you have a program. Skip them, and you have a very expensive scanner. Decision 1. Scope. Be explicit about every one of those 7 layers, and name the environments, production, staging, and the build pipeline itself. The most common failure here is forgetting the pipeline and the cloud control plane. Attackers don't. If it can be reached and it can be weak, it's in scope. Write it down so there's no debate later about whether something counted. Decision 2. Asterisk ownership, and this is where most programs quietly die. Security does not asterisk fix vulnerabilities. Security runs the program. Engineering teams remediate. So map it explicitly. Application code and dependencies belong to the owning dev team. Base images and Kubernetes config usually belong to the platform team. Cloud configuration belongs to whoever owns the account. Use a simple RACI. Responsible, accountable, consulted, informed, so that the moment a finding appears, the system already knows whose queue it lands in. No owner, no fix. Decision 3. Asterisk remediation SLAs. The deadlines that turn good intentions into commitments. Tie them to risk, not just severity. A reasonable starting point. Critical risk fixed within 7 days. High within 30, medium within 90, low on a best effort basis. But add the override that matters most. Anything known to be actively exploited in the wild gets an emergency clock, measured in hours, not weeks. We'll see how asterisk to identify those in the prioritization chapter. The SLA is the single most powerful lever you have. It converts a vague backlog into a dated promise. And an SLA only means something if breaching it has consequences. Otherwise, it's a suggestion. So define the escalation. When a finding approaches its deadline, it nudges the owning engineer. When it breaches, it escalates to their lead. Keep breaching, and it surfaces to leadership on the dashboard. The point isn't to punish people. It's to make organizational friction, not security nagging, the thing that gets a stuck fix unstuck. Usually a missed SLA means the team is under-resourced or blocked, and escalation is how that becomes visible to someone who can actually help. Decision 4. Asterisk exceptions. You will not fix everything, and pretending otherwise just drives risk underground. So build a legitimate path to not asterisk fix, a risk acceptance. But make it honest. It requires a named approver with the authority to own that risk, a documented business reason, a compensating control where possible, and, non-negotiable, an expiry date. An exception with no expiry is just a vulnerability wearing a disguise. Every accepted risk comes back for review. Decision 5. Asterisk how you measure success. Decide your handful of metrics up front, because they shape behavior. We'll detail them at the end, but name them now. Mean time to remediate, percentage of fixes inside SLA, and scanning coverage. What fraction of your assets are actually being assessed? If you measure raw vulnerability count asterisk, you'll incentivize hiding them. Measure speed, coverage, and risk reduction instead. Those 5 decisions, scope, ownership, SLAs, exceptions, metrics, are the skeleton. They take a week of arguing and save you years of chaos. With the program defined on paper, we can start filling it in. And step 1 of any real program is knowing what you actually have. You cannot protect what you don't know exists. The single most common reason a vulnerability goes unpatched is that nobody knew the asset was there. Shadow services, a forgotten staging cluster, an old container image still running in one region. So before assessment, inventory. And in a cloud-native world, inventory has 3 faces. The first face is infrastructure. Pull a live inventory from both clouds. Every cluster, node, load balancer, storage bucket, database, and IAM role across AKS and EKS. The cloud provider's own tools and a cloud security posture platform can enumerate this automatically. The goal? A single list of everything you're running that updates itself, because anything maintained by hand is wrong within a week. The second phase is software, and this is where Cloud Native changes the game. For every service, you generate a software bill of materials, an SBOM, a complete, machine-readable list of every component and version inside that build, using a standard format like CycloneDX. The SBOM is your software inventory. When the next big library vulnerability drops at midnight, the question, are we affected, and exactly where, becomes a database query instead of a week-long fire drill. No SBOM, and you're grepping through repos in a panic. And treat the SBOM as a living thing, not a one-time artifact. Every build emits a fresh one. You store them all in something like dependency track, and that store is continuously re-evaluated against new vulnerability feeds. So you find out you're affected by a brand new CVE without rebuilding anything. The inventory tells you. Attach VX statements, vulnerability exploitability exchange, so you can record, in machine-readable form, yes, this component is present, but our usage isn't exploitable, and stop relitigating the same false alarm on every single build. The third phase is asterisk context, and it's the one tools forget. Each asset needs a business owner and a criticality tier. The service that processes payments is not the internal wiki. When we get to prioritization, is this asset internet-facing and business-critical? Will do more to rank a vulnerability than its raw score ever could. Inventory isn't just a list of things. It's a list of things that matter, to whom, and how much star. This is the heart of it. A vulnerability assessment is how we systematically find and rate weaknesses across all 7 layers. Done badly, it's a noisy scanner that buries your team. Done rigorously, it's a disciplined, layered process where each tool has a job, runs at the right moment, and feeds one consolidated picture. Let's build that process layer by layer. And the organizing idea is shift left. Find each class of weakness at the earliest, cheapest moment it can possibly be caught. Here's the spine of the whole assessment, your delivery pipeline, with a security gate at every stage. Code, commit, build, registry, deploy, runtime. Each gate catches a different class of vulnerability, and a finding gets exponentially more expensive the further right it travels. A bug caught in the IDE costs a developer 2 minutes. The same bug caught in production costs an incident bridge at 3 a.m. We're going to walk this pipeline left to right. Gate 1, at the code layer, static application security testing, SAST. It reads your source code without running it, looking for insecure patterns, SQL injection, that SSRF, hard-coded crypto, unsafe deserialization. The critical move is to run it where the developer lives, in the IDE and on every pull request, so the feedback arrives before the code is even merged. And match the tool to the stack. Your Java, Go, Python, JavaScript, and Kotlin services each need analyzers that genuinely understand that language, not a generic regex. SAST's weakness is false positives, so tune it hard. A noisy gate gets ignored, and an ignored gate is no gate at all. A word on the multi-language reality, because Nimbus has 5. Each language has its own classic footguns, and a good SAST tool knows them. In Java and Kotlin, they share the JVM, its unsafe deserialization and injection. In Python, it's command injection and unsafe YAML or pickle loading. In Node and JavaScript, it's prototype pollution and the NPM dependency jungle. In Go, fewer memory bugs by design, but the same injection and SSRF risks and a habit of ignoring returned errors. The lesson: don't buy one generic scanner and assume it covers everything. Verify it has real, deep rules for every language in your stack. A gate that's blind to your Kotlin service is not a gate. Gate 2, also early, * dependencies, software composition analysis, SCA. Most of your code isn't yours, it's open source you pulled in. SCA reads your dependency manifests, builds the full tree, and flags components with known CVEs. And the part teams miss: most vulnerable dependencies are transitive, not the library you chose, but something it dragged in 3 levels down. So SCA has to walk the whole tree. Pair it with the SBOM we just generated, and ideally with reachability * analysis. Does your code actually call the vulnerable function? Which we'll see can cut the noise dramatically. 2 more checks belong at this early stage. * secret scanning, catching API keys, tokens, and passwords committed into Git, in the history as well as the latest commit, because a leaked cloud key is game over in seconds. And infrastructure as code scanning *. Your Terraform, Helm charts, and Kubernetes manifests are code too, and they encode security decisions. Scan them for the public bucket, the security group open to the world, the pod that runs as root. Catching a misconfiguration in the IAC file is infinitely cheaper than catching it after it's live in 2 clouds. Gate 3, at * build, the container image. When the image is built, scan it with a tool like Trivi, Gripe, or your registry's built-in scanner. It inspects every OS package and language library baked into the image against vulnerability databases and generates an SBOM as it goes. But scanning is only half the job. The bigger win is hardening *. Start from a minimal or distroless base image so there's barely anything to be vulnerable. Run as a non-root user, drop Linux capabilities, and use multi-stage builds so your final image has no shell or package manager for an attacker to abuse. You can't have a vulnerable system package if the package was never there. Gate 4, at the registry and deploy boundary, is where assessment becomes enforcement. Sign your images cryptographically with something like Sigstore cosign, so the cluster can prove an image is really yours and unmodified. Then put an admission controller in front of Kubernetes that refuses to run anything that isn't signed or that carries an unfixed critical vulnerability. This is the moment your assessment grows teeth. A failing scan doesn't just file a report, it blocks the deploy. That's the difference between knowing about risk and stopping it. While we're at the build boundary, raise your sights from, is the image vulnerable, to can I trust this image at all? Supply chain attacks don't bother with a CV. They slip malicious code into the build itself. The answer is provenance. A framework like SLSA gives every artifact a tamper-evident record of exactly where it came from and how it was built. Combined with signing, you get a chain of custody from a specific Git commit to the exact image running in production. So when something looks wrong, you can ask not just, is it vulnerable, but is it even the thing we built, and prove the answer. Gate 5, against the running application, Dynamic Application Security Testing, DAST. Where SAST reads the code, DAST attacks the live app. In staging, the way a real adversary would, with no source access. It finds the things only visible at runtime: broken authentication, misconfigured headers, injection that actually fires end-to-end. For a SaaS like Nimbus, the priority target is the API surface, So point it at your API specs and exercise every endpoint. SAST and DAST aren't competitors. They see different things, and a rigorous assessment uses both. Gate 6, around the platform itself. Posture. 2 scopes. Cloud Security Posture Management, CSPM, continuously checks your Azure and AWS configuration against best practice. The exposed storage, the permissive IAM role, the disabled logging, across both clouds from one view. And cluster posture. Run a tool like KubeBench to score each cluster against the Kubernetes CS benchmark, and check your workloads for dangerous settings, privileged pods, host mounts, missing network policies. The platform layer is where a single misconfiguration can undo every good thing you did in the code. And because Nimbus lives in 2 clouds, know the native tooling on each, because you'll lean on it. On Azure, Defender for Cloud is your CSPM and gives you secure score and misconfig findings. Azure Container Registry scans images. Defender for Containers covers the AKS runtime, and Azure Policy, often via Gatekeeper, enforces guardrails. On AWS, Inspector continuously scans images in ECR and the running workloads. Security Hub aggregates findings against standards, and GuardDuty watches for malicious runtime behavior. The methodology is identical across both. The buttons just have different names. Your job is to normalize both clouds' findings into the one risk register. So are we secure? Never has to be answered twice. Gate 7, in * production, runtime. Everything so far was before things run. Runtime assessment watches what's actually happening. A workload protection tool baselines normal behavior and flags the abnormal. A container suddenly spawning a shell, making unexpected outbound connections, or reading files it never touches. Runtime is also your safety net for the vulnerability you didn't catch and the 0-day nobody could have. It can't always prevent, but it can detect * exploitation in progress. The 7 gates together mean every layer has an owner looking at it. Now, the part automation can't do, and the part that separates a rigorous assessment from a noisy one. * human validation. Scanners produce findings, they don't produce truth. A person has to triage, confirm the real ones, kill the false positives, and spot what no scanner sees. Business logic flaws, and chains, where 3 medium issues combine into one critical attack path. This is also where light threat modeling pays off. Thinking like an attacker about how your specific architecture could be abused. The tools find the known patterns. The human finds the ones that matter to you *. And for a SaaS specifically, give the API its own attention, because the API is the product's front door and the top API risks aren't classic injection. They're authorization flaws. Broken object-level authorization, where user A can read user B's data just by changing an ID in the URL. Broken function-level authorization, where a normal user reaches an admin endpoint. These are business logic bugs a generic scanner sails right past, which is why your assessment must include API-aware testing and, honestly, human review of the authorization model. For multi-tenant SaaS, a tenant isolation failure is the worst day you'll ever have. Assess for it deliberately. One more hard truth about assessment. Your biggest enemy isn't missing a vulnerability, it's noise. A tool that cries wolf 10,000 times trains your engineers to ignore it, and then it misses the real wolf and nobody's listening anyway. So managing false positives is a first-class engineering job, not an afterthought. Tune the rules, suppress the known irrelevant with VX, lean on reachability, and relentlessly measure each tool's signal-to-noise ratio. A scanner your developers trust and act on beats a more thorough one they've learned to mute. Precision is what makes a gate survive contact with a real team. And the final discipline of assessment, * consolidate. 7 layers, a dozen tools, each with its own console and its own scoring. If they stay in 7 silos, no one can see the whole picture, and the same issue gets counted 5 different ways. So pull every finding into one place. A vulnerability management platform or aggregator, deduplicated, correlated to the asset it lives on, and normalized to one scale. Now * you have a single, trustworthy list of everything wrong with Nimbus. Which raises the only question that matters next. Of these thousands of findings, which ones do we actually fix first? Your assessment just produced, let's say, 10,000 findings. Here's the truth that runs the whole program. You cannot fix 10,000 things, and you don't need to. In any real environment, a tiny fraction of vulnerabilities are ever actually exploited, low single digits. The entire game of vulnerability management is finding that slice and ignoring the noise. Prioritization is not a nice-to-have. It is the difference between a program that works and a team that drowns. So how do most teams rank? By CVSS score. Fix the 9s, then the 8s. And it's the wrong instinct. CVSS measures severity, how bad a vulnerability could be in a lab, in theory. It says nothing about whether anyone is exploiting it, whether it's reachable in your build, or whether the affected asset even matters. There are CVSS 9.8s that have never been exploited and never will be, and CVSS 6.5s being used in active ransomware campaigns right now. Severity is an input. It is not the answer. So we add 3 sharper signals. The first, and the strongest, *SYS's known exploited vulnerabilities catalog, the KEV. This is a public, curated list of vulnerabilities with confirmed, in the wild exploitation star. If a finding is on the KEV, the debate is over. It jumps to the front of the queue regardless of its CVSS score, because attackers have already proven it works. KEV membership is the single most valuable yes or no signal you have. Check every finding against it automatically. The second signal, *EPSS, the exploit prediction scoring system. Where the KEV tells you what is being exploited, EPSS tells you what's likely to be star. It's a data-driven model that outputs a probability, 0 to 100%, that a given vulnerability will be exploited in the next 30 days. A CVSS 7 with a 90% EPSS is a fire. A CVSS 9 with a 0.1% EPSS can almost always wait. EPSS lets you act on tomorrow's exploited list, today. The third signal turns scores into a decision. *SSVC, Stakeholder-Specific Vulnerability Categorization, from CISA and Carnegie Mellon. Instead of a number, you walk a short decision tree using your own context. Is it being exploited? Is the affected asset exposed to attackers? What's the impact to your mission if it's hit? Walk the branches and you land on a clear action. Act now, attend to it soon, track it, or defer. SSVC is what forces the abstract scores to collide with your * reality. Now combine them into a funnel and watch 10,000 become 50. Start with everything. Layer 1. Is it on the KEV, or does it have a high EPSS? Those are non-negotiable, straight to the top. Layer 2. *reachability. Does your code actually call the vulnerable path? Tools can emit a VX statement, a vulnerability exploitability exchange, that says present, but not exploitable here, and that legitimately drops huge numbers of findings. Layer 3. Asset context from our inventory. Is this thing internet-facing? Does it touch customer data? A critical vulnerability on an isolated internal test box is not a critical risk star. What survives all 3 filters, usually a few dozen items, is your real work. That's the slice. Let's put real numbers on that funnel, because the scale of the reduction is the whole point. Start with 10,000 raw findings. Drop the ones reachability and VX prove aren't exploitable in your build. Say you're down to 1,200. Now keep only what's on the KEV or carries a meaningful EPSS probability, maybe 380. Finally, intersect with asset context, internet-facing, and business-critical. And you're looking at roughly 50 findings that genuinely demand action this cycle. 10,000 to 50. Same assessment data, but now your team is working a list they can actually finish, aimed at the risk that's actually real. And this is what good looks like on a screen. One dashboard, every finding ranked by risk, not raw severity, blending exploitation, exposure, and business impact. Each row carrying its KEV flag, its EPSS probability, the asset's criticality, and a remediation clock counting against the SLA we set. Research on this layered approach versus fixing by CVSS alone shows roughly an order of magnitude gain in efficiency, the same effort, aimed at the vulnerabilities that actually matter. Your engineers stop bailing the ocean and start closing the doors that are genuinely being kicked. You've got your shortlist. For each finding, there are exactly 3 honest responses: fix it, mitigate it, or formally accept it. Anything else, ignoring it, losing it in a backlog, isn't a fourth option. It's just risk you're pretending you don't have. Let's take the three in turn. Fixing is the real goal. Remove the weakness. Patch the code, upgrade the vulnerable dependency, rebuild the hardened image, redeploy. And in a cloud-native pipeline, the best fixes are automated. A bot that opens a pull request bumping the vulnerable library the moment a patch exists, runs your tests, and lets a human merge with one click. Because your deploys are already automated, a fix can go from patch available to live in both clouds in hours, not change control weeks. That speed is the whole advantage of being cloud-native. Use it. One caution on speed. Fast must not mean reckless. A security patch is still a code change, and a botched emergency fix that takes the product down can be worse than the vulnerability. This is where cloud-native gives you a gift: progressive delivery. Roll the patch version out to a small slice of pods first, watch your health and error metrics, and only promote to 100% when it's proven stable. If it misbehaves, roll back in seconds. You get to move fast and safely because Kubernetes makes a controlled, reversible rollout the default rather than a heroic effort. Sometimes you can't fix immediately, no patch exists yet, or the upgrade is risky. Then you mitigate, reduce the risk without removing the bug. A virtual patch, a WAF rule that blocks the exploit pattern, a network policy that cuts the workload off from anything it doesn't need, tightening that overpermissive IAM role so a compromise goes nowhere. Mitigation buys you time and shrinks the blast radius, but log it as a temporary control with the real fix still tracked behind it. A mitigation that quietly becomes permanent is how today's workaround becomes next year's incident. The third response, accept, we already designed, the time-boxed risk acceptance with a named owner and an expiry. The mechanics that make all three work. Every prioritized finding becomes a ticket, automatically routed to the owning team from our RACI, landing in the tools developers already use, with the SLA due date attached. No spreadsheets. No, the security team will email you. The finding shows up in the same backlog as the feature work, with a clock. Remediation isn't a separate universe. It's just well-routed, well-dated engineering work. A vulnerability is not closed when a developer says, done. It's closed when you've proven it's gone. So every remediation gets verified, rescan the asset, and confirm the finding is actually absent. This catches the fix that didn't deploy, the patch that covered one of three affected services, the change that got reverted. Trust, but verify, and automate the verification so closure is a fact in your data, not a hopeful checkbox. Verification also has to catch the sneakiest failure mode, regression. A vulnerability you fixed 3 months ago quietly returns. Someone pinned an old dependency. A base image rolled back. A config got reverted in one cluster, but not the other. Because your assessment is continuous and tied to history, a returning finding gets flagged as exactly that, a regression, not a brand new issue, and routed back with the context of how it was fixed last time. Closing a vulnerability once is good. Making sure it stays closed is what continuous verification is actually for. And then, it never stops. New code ships, new CVEs drop against libraries you already use. The cloud config drifts. The same loop runs again, continuously, automatically, at the speed of your pipeline. Point-in-time security is a myth in a system that changes every hour. The program isn't a quarterly event you survive. It's a background hum that keeps your real risk flat even as your software and the threat landscape never stop moving. You can't manage what you don't measure, and the metrics you choose will quietly steer your whole team's behavior, so choose carefully. For that matter, mean time to remediate, how fast you actually close things, by severity. SLA compliance, the percentage of fixes that landed inside the deadline. Coverage, what fraction of your assets are even being assessed, because an unscanned asset is an unknown risk, not a zero risk. And risk burn down, is the total weighted risk trending down over time? Notice what's missing, raw vulnerability count. Measure that, and you teach people to hide findings. Measure speed, coverage, and risk reduction, and you teach them to close them. And balance two kinds of metric, because together they tell you if the program is actually getting better, not just busy. Lagging indicators look backward. Your MTTR, your escape vulnerability count, the issues that reach production. Leading indicators predict the future. What percentage of findings your leftmost gates catch before merge? Your mean time to detect a newly disclosed CVE in your estate. Your scan coverage trend. When your leading indicators improve, your lagging ones follow a quarter later. Watch the leading ones to steer, report the lagging ones to prove it worked, and report to each audience in their language. Engineers need the actionable list. These findings on these services due these dates. Leadership needs the trend and the story. Is risk going up or down? Are we meeting our commitments? Where do we need to invest? Same underlying data, two very different views. The executive dashboard is also how you keep the program funded. A clear risk burn-down chart is the most persuasive budget request a security lead can bring to the table. And rapid in governance. A regular review. Monthly is sensible, where owners walk their overdue items, exceptions get re-examined before they expire, and the program itself gets tuned. Are the SLAs realistic, or are teams constantly blowing them? Is one service a chronic source of findings and needs deeper help? The metrics don't just report the program, they improve it. The loop you measure is the loop that gets better. None of this survives contact with reality unless the culture supports it. And the heart of the culture is one idea. Make the secure path the easy path. Every gate we built leans left, toward the developer, for a hard economic reason. The cost of fixing a flaw rises steeply the later you catch it. 2 minutes in the IDE, a code review comment at commit, or a production incident. Same bug, wildly different price. Shifting left isn't a slogan, it's just cheaper. But there's a trap. If security is nothing but gates that block developers, they'll route around you. And a control everyone bypasses protects no one. So favor guardrails over gates. Automated, fast, low-friction checks that guide developers to safety with clear fixes, and reserve the hard blocks for the genuinely critical. The unsigned image, the actively exploited CV, the leaked secret. Fast feedback, clear remediation, and a sensible threshold for what actually stops the line. Friction is the enemy of adoption, and adoption is the whole game. And finally, vulnerability management is not a thing the security team does to engineering. It's a thing the whole organization does together. Security owns the program, the tooling, the standards. Engineering owns the fixes. Platform owns the foundation. Plant security champions inside the dev teams. Engineers who carry context both ways. When developers see vulnerability data as useful feedback on their own work rather than an audit from outside, you've won. Shared ownership is what turns a process into a culture. Let's make all of this real by following one vulnerability through the entire loop. Because the test of a program is not the diagram. It's what happens at 2 in the morning when a serious one lands. Picture it. A critical remote code execution vulnerability is disclosed in a wildly popular Java logging library, the kind of thing that hits half the internet at once. Think Log4Shell. The clock has just passed midnight. In a company without a program, this is the start of a week-long panic. In ours, it's a Tuesday. Watch the difference. Step 1. Am I even affected, and where? No login to 12 repos and grep. We query the SBOMs. In seconds, the vulnerable library is present in 2 of our 12 services, the Java Payments service and, surprisingly, the Kotlin service, both pulling it intransitively through a framework. We know the exact versions, the exact images, and which clusters they're running in, across both AKS and EKS. The week-long "Are we affected?" fire drill just became a 30-second database query. That is the entire payoff of the inventory discipline. Step 2. How urgent really? We check the 2 signals that cut through panic. Is it on SYS's KEV catalog? Yes. Confirmed exploitation in the wild. EPSS. 97%. There's no debate to have and no meeting to schedule. This trips the emergency lane in our policy automatically. The 24-hour clock starts. Meanwhile, the half of the internet without this program is still arguing about whether a 9.8 deserves attention. Step 3. Context sharpens it further. Reachability analysis confirms our code actually reaches the vulnerable function. This isn't a dependency sitting dormant. And the asset context from our inventory lights up. The payment service is internet-facing and Tier 1 critical. Every signal points the same way. This is genuinely act now, not someday. Note how the same machinery that deprioritizes thousands of false alarms is exactly what gives us total confidence to drop everything for this one. Step 4. Fix and contain fast. The automated path opens pull requests against both services, bumping the library to the patched version. Tests run green. While the fix is in review, we don't sit still. We mitigate. A WEF rule blocks the known exploit string at the edge in both clouds, and the admission controller is set to reject the vulnerable image so it can't be redeployed by accident. Tickets land directly in the payments and mobile teams boards, emergency flagged, owners already attached from the RACI. Fix in flight, blast radius already shrinking. Step 5. Verify and close. The patched images are signed, deployed across both clouds through the normal pipeline. Hours, not change control weeks. Then we prove it. Rescan both services and confirm the finding is genuinely gone, in every cluster, not just one. The ticket's close on evidence. The risk burn down chart ticks down. And by sunrise, while a lot of companies are just discovering they were affected, ours has already found it, fixed it, contained it, and verified it, because we didn't react to a crisis. We ran a loop that was already running. That is what a program buys you. Before we close, the 5 ways these programs fail. Learn them so you can dodge them. 1. Confusing scanning with managing. A report is not a fix. 2. Prioritizing by CVSS alone and burning out on noise. 3. No clear ownership, so findings rot with no name attached. 4. Point-in-time assessments in a system that changes daily. And 5. Gates so heavy that developers route around the whole program. Every one of these is a process failure, not a tooling failure, which is good news, because process is something you control. So here's the checklist to take back to your team. The shape of a rigorous program on one screen. Scope all 7 layers, not just the code. Put a gate at every pipeline stage and shift them left. Prioritize with KEV, EPSS, and SSVC, never severity alone. Set remediation SLAs by real risk, with an emergency lane for what's actively exploited. Autoroute every finding to a named owner. Verify every fix by rescanning. And measure speed, coverage, and risk burn down, never raw count. Run that loop continuously, and you have a real program. Let's bring it home. Vulnerability management is a continuous loop. Inventory what you have, assess all 7 layers, prioritize by real-world risk, remediate against a deadline, verify the fix, and measure the whole thing. Then turn the loop again. The vulnerability assessment is the engine inside it, but the program, the ownership, the SLAs, the prioritization, the culture, is what actually moves your risk down and keeps it there. The flood of vulnerabilities is never going to stop. But you don't have to bail the ocean. You just have to build the system that finds the few that matter and closes them on time, again and again. Build the program, automate the loop, and let the noise wash past. If this gave you a blueprint you can use, subscribe to EvoluGuard Academy and go make your defense evolve. See you in the next one.